Material analysis by nuclear techniques. In this lecture, we shall try to understand the basic principles and requirements for the material analysis by nuclear techniques. We shall address the general experimental setup, mathematical basis, and nuclear reaction kinematics. We come across various types of material samples in different contexts. Often, it becomes necessary to know what are the various constituent elements present in such samples, as well as the amounts of these elements. The procedure adopted for getting such information is generally referred to as material analysis or elemental analysis. Material analysis has two aspects. The first aspect is the qualitative one, wherein the information aimed at is the identity of the various elements present in the sample. The second aspect is the quantitative one. Here, we require either the absolute amounts of the elements or their relative amounts with respect to some reference element. Depending on the percentage abundance of the constituent elements, they may be classified broadly into two categories: macro elements with abundance greater than about 1% or so, and micro elements with abundances less than about 1%. However, such a classification is not at all unique. A certain element may be a macro element in one sample, whereas the sample element may be a micro element in another sample. As an example, consider the case of carbon. It is a macro element in biological samples, but it is a micro element in steel. An important class of elements whose abundance is extremely small, of the order of 1 in 10 raised to 6 or lower, is known as trace elements. Their concentration is usually expressed in units of parts per million ppm or parts per billion ppb. These can be included along with the micro elements, but because of their great importance, they are regarded as belonging to a separate category. A large number of samples can be cited to bring out the relevance and significance of such trace elements. All the other elements, apart from the micro or trace elements, can be analyzed and said to form the matrix. A number of techniques have been developed over the past few decades for the qualitative and quantitative estimate of various elements. Neutron activation analysis, NAA in short, Rutherford backscattering, RBS in short, X-ray resonance fluorescence, XRF in short, atomic absorption spectroscopy, AAS in short, and proton-induced X-ray emission, PIX in short, are some of the important ones. The ongoing discussions will cover neutron activation analysis, Rutherford backscattering, and proton-induced X-ray emission. Basic principles of elemental analysis. An analytical technique for the constituent elements of a sample requires that there should be some characteristic and measurable property of the particular elements present in the sample, which can act as a fingerprint of the element. It should be possible to distinguish between various elements on the basis of this property. Usually, it is some measure of the property which will characterize the element. This forms the qualitative part of the technique. It should also be possible to define an intensity of the property which should be proportional to the quantity of the element in the sample. For example, if the characteristic property is a photon emitted from the sample, the energy of the photon will identify the element and the number of photons emitted per second which is directly proportional to the intensity, will yield the quantitative information. The characteristic property that we have been mentioning can be chemical, atomic, or nuclear. Chemical methods make use of the chemical properties of the elements. Such methods involve elaborate chemical treatments with various reagents. The atomic spectroscopy method rely on characteristic spectra, which could be emission or absorption of the elements. And nuclear techniques involve detection and measurement of characteristic radiations or particles emitted from the nuclei of the constituent elements. The basic requirements of elemental analysis. The main requirement for any elemental analytical technique, of course, is the sensitivity. This may be defined as the smallest change in the amount of an element in the sample, which will produce a detectable change in the property being used as the basis of the technique. It is usually expressed in parts per million or ppm. The sensitivity, of course, will depend on the element and the technique, and very often on the major bulk of the material other than the trace element of interest called the matrix. The second requirement is the minimum detection limit. This is the smallest absolute amount in microgram or concentration in ppm of the element, which will yield a detectable measure of the property. A minimum detection limit is also dependent on the element, the matrix, and the technique. Another requirement is regarding the multi-elemental nature of the technique. Some of the methods for elemental analysis can simultaneously give information on several elements. These methods are called multi-elemental methods. In many cases, the multi-elemental nature may be very important, since a single analysis will yield quantitative information on many elements, thus saving valuable time which would have been required if the method was not of this nature. Under certain circumstances, after the analysis is over, we would like to preserve the sample for later use. It becomes very much essential that subjecting the sample to the analysis by the particular technique should not destroy it. And this requirement is called the non-destructive nature. General experimental setup. In the experimental setup, we need to have a source which produces a narrow beam of incident radiations like X-rays, gamma rays, etc., or particles, electrons, protons, alpha particles, etc., of the required type and energy. The number I, called the flux of the incident radiations per particles crossing unit area of the beam per second, will be either known or can be measured or can be eliminated from the calculations. Either radioactive sources for alphas, gammas, or X-rays and electrons, or particle accelerators for energetic charged ions can be used as source depending on the particular technique used for the elemental analysis. The sample or target is usually in the form of a thin, circular disc, preferably of uniform thickness. It contains the various elements which have to be qualitatively and quantitatively estimated. The target normally contains macro, micro, and trace elements. The nuclear techniques are used for the micro and trace elements. Preparation of the target is an important aspect of any technique of elemental analysis. The simplest case would be for a material for which a thin, self-supporting target can be made. Very often, a self-supporting target may not be feasible. In such cases, the target is made as a deposit of the material onto a suitable backing material. The backing should be thin and made of a material that will not produce intense background radiations which would interfere with the elements of interest in the sample material. Thin target and backing are specially necessary in techniques which make use of energetic charged particles which would lose a part of their energy in the target. Also, radiations like X-rays can be heavily attenuated in the target if its thickness is not small. The ions penetrate the target and are allowed to be collected by an insulated Faraday cup which is connected to a charge integrator. The total charge collected would be Q equal to I times Q, where I is the number of incident ions and Q is their charge. Detectors. The elemental analytical technique depends on the particles or radiations emitted from the target on being bombarded by the incident projectiles. These outgoing particles or radiations are detected by means of suitable detectors. The detector has an active medium on entering which the particle or radiation interact with the atoms and produce or lead to the production of ion pairs. The ion pairs are collected by the electrodes, thereby producing electrical signals. One of such signal will be available at the output of the detector for each incident radiation, the amplitude of the signal being proportional to the energy which the incident radiation deposits in the active medium. The type of the radiation and its energy usually identifies the element, and the number of such signals produced per incident radiation gives a measure of the amount of the particular element. The resolution of the detector. Since the amplitude of the detector output signal is proportional to the energy deposited in the detector, we would expect a sharp line in the pulse height spectrum of monoenergetic radiations falling on the detector as shown in the figure. However, since the various processes leading to the formation of the detector signal are statistical in nature and are subject to statistical fluctuations, the spectrum spreads into a Gaussian peak with a finite width. This peak is often referred to as the photopeak. The width of the peak at half maximum is often quoted as representative of the resolution of the detector and is referred to as the full width at half maxima. The full width at half maxima is very important in situations when there are close-lying peaks in the spectrum. That is, when the incident radiations are not monoenergetic and contains close-lying radiation energies. How well the peaks can be distinguished depends on the resolution. The narrower the peak, the better is the resolution. Quantitatively, the resolution is expressed as a percentage of the peak amplitude V0. Thus, the resolution R is equal to FWHM over V0 times 100. For charged particles and low energy X-rays, the pulse height spectrum contains only the main peak. However, for higher energy X-rays and gamma rays, in addition to the main peak, the so-called photopeak, there is additional continuous distribution of lower amplitude pulses. This is due to the Compton scattering interactions within the detector, in which the scattered gamma ray escapes from the detector volume and hence do not contribute to the energy deposited in the detector. The lower amplitude pulses contribute to the so-called Compton distribution. The area under the photopeak is a measure of the number of outgoing radiations. The type of detector to be used will be decided by the type of the particle or radiation to be detected. If we are to detect charged particles like protons, alpha particles and other heavy ions, we can use silicon surface barrier detectors. If it is X-rays, we can use lithium drifted silicon detectors. If it is gamma rays, the detectors can be sodium iodide detector or germanium detectors. Another important aspect with regard to detectors is the detection efficiency. Detection efficiency is defined as a fraction of all incident photons which are actually detected by the detector. This is rarely won since photons have only a finite probability of interaction inside the detector volume. Those photons which do not interact within the detector volume are obviously undetected. When detection efficiency is of importance, thallium-doped sodium iodide detectors are used. When high resolution is needed, we will go for germanium detectors. This figure shows the electronic setup used for detector signal processing and counting. The output signal of the detector may not be of the right amplitude and shape to be counted directly. It needs amplification and pulse shaping, and suitable electronics have to be used for processing these detector signals. The preamplifier, which is kept close to the detector using a very small length cable, will be either of the charge sensitive type or voltage sensitive type. It will have high input impedance and low output impedance so that the signal can be driven through long output cables if required to the main amplifier. The gain of the preamplifier is not significant. The major amplification of the signal is provided by the main amplifier, also referred to as a linear amplifier. The main amplifier also provides pulse shaping, resulting in a near Gaussian output pulse with a tail on the trailing edge. The gain and pulse width can be adjusted in this case, and typical range of the pulse width is from 0.5 microsecond to 10 microsecond. Multi-channel analyzer. This unit analyzes the signal and provides a digital output proportional to the amplitudes. The pulse height spectrum is in the form of counts versus channel number. The channel number is proportional to the amplitude of the signals, thereby to the energy of the radiations incident on the detector. Finally, the MCA output is fed to a personal computer through an interface card to determine the amount of elements in the irradiated sample. Useful nuclear processes for material analysis. In elastic scattering, there is no internal excitation of the colliding partners, and the kinetic energy in this case will be conserved. The elastically scattered particles at certain angle are detected and their energy and flux are measured. The measured energy is an indication of the atomic mass of the scattering element in the sample, and the flux is an indication to the amount of the element. The best example of a technique based on elastic scattering is the Rutherford backscattering or RBS. Inelastic scattering. In this process, there is a loss of total kinetic energy. The lost kinetic energy goes into internal excitation of the colliding partners. The excitation could be atomic or nuclear. During the inevitable decay of the excited system, the excitation energy will be emitted either as a quantum of radiation, and this is known as radiative decay, or as a particle. The particle emission is possible only if the excitation energy is above the particle emission threshold. The type and energy of the outgoing radiation or particle identifies the element, and their number measures the quantity. An example of inelastic scattering technique is the proton-induced X-ray emission or PIX. Nuclear reactions. Here, the interaction between the incident projectile and the target nucleus results in the emission of a third particle or radiation, the target nucleus getting transformed into a new species. The qualitative aspect of the technique relies on the type and energy of the outgoing particle or radiation, and the quantitative aspect is based on the number of these outgoing particles or radiations. The nuclear techniques depend on the production of induced radioactivity in the sample on bombarding with the projectiles. Depending on the half-life of the induced activity, the techniques can be broadly classified into two: online analysis and offline analysis. Online analysis. When the half-life is very small, typically less than milliseconds, the outgoing radiations are counted in the detector at the same time as the irradiation is proceeding. As a result, the detector has to be placed near to the irradiation setup. Offline analysis. In some cases, the half-lives involved are larger and counting has to be done sometimes after the irradiation is over. Also, when carrying out the neutron activation analysis using reactors, it becomes impossible to keep the detector near the reactor because of the larger neutron background. The sample after irradiation will be taken away from the irradiation setup to the so-called counting room, and the outgoing radiations will be counted there. Mathematical basis of the quantitative estimate. The probability of the occurrence of an atomic or nuclear interaction is often expressed in terms of a quantity known as cross-section of the relevant interaction. It is often denoted by sigma and is expressed in centimeter square. The most common unit used in the atomic and nuclear regimes is Barnes, defined as 10⁻⁻24 centimeter square. The relevant cross-section useful in the nuclear analytical techniques is the probability for observing a certain outgoing particle at a particular angle with respect to the incident direction per incident particle per target nucleus. Consequently, sigma is a function of the angle of observation theta. We indicate this by writing the cross-section as sigma theta or as d sigma, which is a function of theta, by d omega. And this quantity is known as the differential cross-section per unit solid angle at angle theta. The total cross-section will then be given by an integral over all solid angles and sigma equal to integral d sigma theta over d omega times d omega. The number of outgoing particles detected at an angle theta turns out to be Ni equal to I times Nt d sigma theta over d omega times omega d eta t. In this equation, I is an incident flux of the projectiles, which is the number of particles per unit area of cross-section of the beam per second. Nt is the total number of atoms or nuclei of the element in the sample. Omega d, the solid angle subtended by the detector at the target center. Eta, the detection efficiency of the detector. And T, the correction factor taking into account relevant attenuation of the outgoing beam. A measurement of Ni and knowledge of all other factors yields Nt. The rate of production of nuclei due to the projectile bombardment is given by dNp over dt equal to R minus lambda npt. Here Np is the number of excited nuclei at a certain time t. R is the rate of production due to the projectile bombardment, which is equal to I times Nt sigma, and lambda is the decay constant of the radioactivity produced and is related to the corresponding half-life tau as natural logarithm 2 over tau. Assuming that the irradiation is started at time t equal to 0, we have npt equal to r over lambda times 1 minus e raised to lambda t. We will consider two cases, online analysis and offline analysis. In online analysis, the half-life is very short and lambda times npt is very much greater than r. That is, the excited nuclei decay as fast as they are produced, and the rate of emission of the outgoing particles is given by R equal to I times Nt sigma. In the offline case, the half-life is comparatively longer, and therefore lambda times npt is less than R. That is, the excited nuclei decay rather slowly. Suppose the irradiation is stopped at time t equal to tr and the counting is done at time t equal to tc. In that case, nptc equal to r over lambda 1 minus e raised to lambda tr e raised to minus lambda tc minus tr. And the rate of emission of the outgoing particles is given by r prime equal to lambda times nptc. The sample will definitely contain many other elements which will also give out radiations or particles which will interfere with those from the element of interest. These radiations form the background radiation, in the presence of which the radiations of interest have to be distinguished and counted. If the radiations from the various elements are clearly separated in energy and well above the general background level, there is no issue. In fact, such a case presents the multi-elemental feature of the technique, and all the elements can be simultaneously determined. If not, the sample might have to be subjected to chemical separation treatment either before irradiation, that is pre-irradiation treatment, or after the irradiation, post-irradiation treatment, or both. Nuclear reaction kinematics. The qualitative identification of the various elements in a sample depends on the energy and type of the outgoing radiation or particle. It is necessary to relate energy of the outgoing particle to the mass number or atomic number of the projectile. For techniques relying on some type of nuclear reaction, the relevant relations can be derived by invoking the conservation laws for momentum and energy. Let us consider a nuclear reaction that is designated as A plus X giving B plus Y plus Q. In this case, A is the projectile with mass MA, X is the target with mass mx, and B is the outgoing particle with mass mb, and Y is the residual nucleus with mass my. And Q is the Q value of the nuclear reaction. The kinetic energies are usually much small compared to the rest mass energies of the particles, and consequently, we are justified in using non-relativistic equations. Also, Ma plus mx is approximately equal to mb plus my, which is equal to capital M. And from the conservation of energy, we can write Ea plus Q equal to Et, which is equal to Eb plus Ey. And from this, the Q of the reaction can be written as Eb minus Ea plus Ey. When we write the conservation of momentum, we have square root of 2 ma Ea equal to square root of 2 mb Eb cos theta plus square root of 2 my Ey cos phi. Also, 0 equal to square root of 2 mb Eb sin theta plus square root of 2 my Ey sin phi. And from equation 3.1, we have square root of 2 my Ey cos phi equal to square root of 2 ma Ea minus square root of 2 mb Eb cos theta. And from equation 3.2, we have square root of 2 my Ey sin phi equal to negative of square root of 2 mb Eb sin theta. Squaring and adding equations 4.1 and 4.2, we get a new expression for 2 my Ey. In the next step, we have eliminated the constant factor 2 on both sides of the equation. The next step is to write the equation for Ey. The Q of the reaction is given by Eb minus Ea plus Ey, that is Eb minus Ea plus equation 6. A rearrangement of the equation gives EB times 1 plus MB over MY minus EA times 1 plus MA over MY minus 2 over MY times square root of MA MB EA EB times cos theta. This equation can be represented as a quadratic in square root of EB. When we do that, we'll get equation 8. And the equation for its solution is x equal to minus b plus or minus square root of b square minus 4ac over 2a. When we do that, we can find out square root of EB as given by this equation. Note that MA plus MX is approximately equal to MB plus MY, which is equal to capital M. Since a quadratic equation is involved, the condition for real discriminant can be stated as a condition for the angle sin theta equal to My over Mb times M by Ma times 1 minus Q by Ea minus 1. Marian and Young have published equations and tables relevant for nuclear reaction analysis. They define the following quantities: A equal to Ma times My over M square times Ea over Et, B equal to Ma times Mb over M square Ea over Et, and C as equal to Mx times Mb times 1 plus Ma Q over Mx Et, and D as equal to Mx times My times 1 plus Ma Q over Mx Et. Note that A plus B plus C plus D equal to 1 and AC equal to BD. In terms of A, B, C and D, the energy of the outgoing particle can be shown to be given by the following relation. That is EB over ET equal to B times cos theta plus or minus square root of D over B minus sin square theta. It is often useful to work in the so-called center of mass system of coordinates. This is because in the center of mass system, one is interested only in the relative motion of the particles involved in the interaction. Any theoretical model treats only the relative motions, and the cross-sections calculated from the model are invariant in the center of mass system. Finally, when a comparison is to be made with experimental results, a conversion from the center of mass system to the laboratory system becomes necessary. Relation between the angles in the two systems is given by sin theta equal to square root of EB over D times ET sin theta Cm. In terms of the center of mass angle, the energy of B is given by EB over ET equal to B plus D plus 2 square root of AC cos theta Cm.